Hello, in this video we're going to look at Maclaurin and Taylor series. We've looked at Taylor polynomials previously, now we're going to take that to an infinite series. So just to review, this is just like a Taylor polynomial, only now I'm going to infinity instead of stopping at a particular value. So the formula is the same. I'm doing the kth derivatives of f evaluated at a given value x naught divided by k factorial, and then times x minus x naught to the k. So you can see what it looks like if we expand it out here. So that is a Taylor series. Big difference here is now I have a dot, dot, dot at the end, indicating that this goes on forever. And for Maclaurin, it's just a special case of the Taylor series where x naught is 0. So it just simplifies a little bit here because I don't have the x minus x naught anymore since x naught is 0. Okay, so let's do an example with this and see what we can do, how we can get the Taylor series approximation of a function to start. So I've got the function cosine of 2x centered at x equals 0. So this is Maclaurin series. And they first want me to find the first 4 non-zero terms of this series. Okay, so some of these terms might end up zeroing out. So I want to make sure I end up with 4 terms that are not 0 before I stop coming up with terms. So just like when we did the polynomials, I start with the function and its derivatives, and then evaluating those at our x naught value. So if I plug in x naught, or 0, in for x naught, in here for the original function, cosine of 0 would be 1. And then taking its derivative of cosine is negative sign, and then don't forget to do chain rule here and multiply by the derivative of 2x as well. So I end up with the first derivative, which is 0. Okay, so I'm already getting some 0 values. The whole term where k equals 1 is going to end up being 0. So I'm not going to be able to stop at just the fourth derivative here if I keep getting these 0 terms. We'll do a couple more derivatives, remembering to do chain rule each time, and then I plug in 0, and there's another 0 term. So far I've only got 2 values that are non-zero coefficients. So I got to keep going until I get 4. So a few more. You can see how the notation changes if you're wondering how to do like a 4th, 5th, and 6th derivative notation. This is one option. There are others like Roman numerals that you could do, but this one's a nice, convenient one. So this is the 4th, 5th, and 6th derivatives, and I finally have 4 non-zero values that I'm going to be able to plug in and get 4 non-zero terms. Okay, so just a refresher, here's the formula we're plugging into, and this kth derivative of f at 0 are the values I have here. I'm going to plug in all of them, including the zeros, just so we get the k's right in each term. So it looks like this. So 1 over 0 factorial times x to the 0, 0 over 1 factorial x to the first, and so on, just adding those values. And really the only thing left to do at this point is to clean it up a little bit. All of these odd numbered terms are going to 0 out, so I'll drop them out, and then I'll simplify the coefficients for the even powers. And I end up with this for my final answer. That is the Maclaurin series, the first 4 terms. And of course, this is infinite, so I include that ellipses, the dot, 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 at the end here to indicate that it keeps going. Okay, so let's look at some other things that we can do with these Taylor and Maclaurin series. One is I can come up with the summation notation for this. So I'm looking for a pattern. And here, in this particular one, it's easier to see the pattern before I simplified the coefficients. Sometimes it's easier after, so it's nice to have both of those written out so you can figure out what the pattern is. And I'm really just taking this piece by piece. I want to be able to write a general nth term for this that will describe all the terms of this series. And I'm ignoring all the 0 terms because they don't show up. So I take it piece by piece, maybe starting with the x terms. So I notice that each time, each x power is even. And so I need to write the exponent so that I will always get an even value there. And the quick way of doing that is using a 2n. If I do x to the 2n power, then no matter what n is that I'm plugging in, I will always get an even value for the exponent. So that's going to be one piece of it. My same thing for the factorials. Those are all even. So I would want a 2n factorial at the bottom. And then it looks like I'm squaring, or I'm increasing the exponent actually on the 4. This is 4 to the first. This is 4 squared. This is 4 cubed. So I'm going to need a 4 to an n in here. And then the last piece is the alternating sign. So I'm going to need a -1 to an n, or an n plus 1, or something like that in here. So if I put all that together, I end up with this here. So ended up just writing 4 is 2 squared. So I was able to write these together as 2x to the 2n. And then there's that factorial being even and the alternating sign. Now this is a tricky thing. You want to give yourself time when you're developing these. It's a lot of just like identifying those patterns, putting the pieces together, and then testing it out. So I might come up with something like this or something similar, and then I would start plugging in the values of 0 to this to see if it matches the series that I have, just to verify that I've got it right. And oftentimes I'll be close but not have all the details quite right, and so just testing it will help me to figure out how to tweak this nth term so that it does match perfectly with the series. Okay, so it's a little bit of trial and error. Give yourself some time and practice it. So here I might double check myself and say, okay, if I plug in 0, -1 to the 0 would be +1, 2x to the 0 would be 1, and 2 times 0 would be 0 factorial, which is 1. So everything is 1, which matches my first term. So I'm feeling pretty good about that. And then I might check one or more. So n equals 1, this would be -1, which mine is negative, looking good. 2x to the second power, so that would be 4x squared. And 2 times 1 would give me a 2 factorial in the denominator. So it's matching up good. I feel good about my summation notation here, and I can move on. Okay, so something else that I can do with the Taylor series is come up with the power series representation of a given Taylor series using a common series that I have. So for instance, on this last one, we just figured out what cosine of 2x is equal to. I took this function and was able to rewrite it as an infinite series. Just if you stop and think about it, it's pretty cool. But we have a lot of these common ones, and you'll find them in the notes for this section that are written out, that we've already found this summation notation for them. And so we can use that to shortcut with variations. So if you look at that common list in your notes, you'll see that there's a tangent inverse of x power series notation. And it looks something like this. Okay, and so they went through the same process we just went through in that last example to come up with this. And we're just going to use it as a shortcut for this particular one. So what I do is I start with the original series, and I look at the differences. Well, I have a 5 multiplying out front, so I can take this series and multiply it by 5, and that'll take care of that piece of it. And in place of x, I have an x squared. So in the series notation, I'm going to take the x and replace it with x squared. So it looks something like this. This is my 5 out front. I can put it inside the summation if I want it as well. And then I have an x squared in here. So I found a series notation for 5 tangent inverse of x squared. I'm just going to clean it up a little bit by taking care of this, the exponents here by multiplying. So that ends up, if I distribute the 2 to the 2n plus 1, I get x to the 4n plus 2. And then I have a series notation for it without having to go through all that trouble. On the assessment, on the exam, I'm going to have you do both methods, so it's a good idea to practice using this shortcut and using the original series formula. Okay, something else I can do is I can find the sum of a series using those common representations. So here I have a series, and I need to find the sum. And so I'm going to look at that list of common representations, and I'm looking for one that has the same characteristics as this one. For instance, it's got an n in the denominator. It has something with an exponent on it. Okay? Those common power series representations are going to have an x in there. So I'm just looking for something similar. I also want to see some kind of alternating -1 in there as well. If you go through that list, you might want to pause and take a look at it right now and see if you can decide which would be the right one. But this is the one that I picked. It's very similar. I have an nth power, I have a -1 to a power, and I have an n at the bottom. And from here, I'm just going to take my original series and I'm going to manipulate it to look as much like this summation as I possibly can. And then I can equate it to some kind of natural log from there. So if I take that original series, I have a 2n power here. This one was just to the n, so I want to separate that out. And then there's no 3 in this natural log, so I pulled that out. Since it's in the denominator, it becomes a 1/3. So I pulled that out. And so the 4 squared to the n is what I get here in addition to that 1/3 bringing out. And now it looks just like the natural log of 1 plus x, only I have a 16 where the x is, which means that my series would be equal to 1/3 times the natural log of 1 plus 16, because that's what the x is here. So I get 1/3 natural log of 17. I was able to, using this, take an infinite series and find a finite value for it. So pretty cool. Okay, so those are the things that you can do with Taylor series, and here is a couple of examples for you to practice on your own to try this out.